For years, the standard approach to sequence modeling relied on recurrent neural networks, but these models have a structural bottleneck. They are forced to process data sequentially, taking in inputs one at a time. Because each hidden state depends on the computation of the previous step, this architecture inherently precludes parallelization. When you scale up to longer sequences, memory constraints limit batching, and training grinds to a halt. In 2017, the transformer architecture bypassed this bottleneck, achieving a 28.4 Blue score on the WMT 2014 English to German translation task, and outperforming all existing models, including robust ensembles. The architecture reached this mark by dispensing with recurrence and convolutions entirely. Instead, it relied on a mechanism called self-attention to draw global dependencies between the input and output sequences. The mathematical engine driving this is scaled dot-product attention. It takes an input sequence and computes compatibility weights by knobing a set of query vectors against a set of key vectors. But while basic self-attention eliminates the sequential time delay, applying it as a single monolithic function imposes a mathematical constraint when attempting to resolve the competing patterns found in human language. Scaled dot-product attention requires 3 vector inputs: queries, keys, and values. The network computes dot products to determine alignment, scaling the result by the square root of the key dimension. This passes through a softmax function, converting raw values into normalized weights. In a single-head architecture, this softmax operation ultimately applies these weights to the values, outputting a single averaged weighted sum for the given token. Here lies the bottleneck. Words possess multiple relationships simultaneously, like a syntactic link to a verb and a semantic link to a pronoun. A single attention function forcefully averages these distinct signals together into one uniform output. Human language does not operate on a single metric of relevance. It functions as a layered system of concurrent, distinct rules operating in tandem. To capture these nuances without averaging them into static noise, the model must mathematically fracture its attention mechanism into parallel dimensions. We start with the baseline dimension of an input token embedding vector in the transformer model, set at 512. This schematic shows multi-head attention, the architectural solution to the averaging problem. Rather than running one massive attention function, it executes several in parallel. The first step is to linearly project the original query, key, and value matrices. The model uses learned parameter matrices to project the original 512-dimensional vectors into new, lower-dimensional spaces. Specifically, it projects them down to dimensions of 64 for the keys, queries, and values. This entire projection process is executed simultaneously across 8 completely separate parallel streams, or heads, in the base model. Because each of these 8 streams uses different learned weights during projection, they remain mathematically isolated from one another. These isolated linear projections give the model separate, dedicated workspaces to examine distinct linguistic features without cross-interference. Next, the architecture applies the scaled dot-product attention algorithm to each of the 8 new subspaces simultaneously. Operating in unique subspaces means these heads can attend to completely different positions in the input sequence. One head maps out grammatical syntax, while another maps contextual semantics. Unlike the single-head model, these distinct signals remain crisp. They are no longer diluted by a single softmax averaging process. Structurally, multiplying the number of attention functions by 8 might seem like an engineering paradox that would multiply the computational cost. However, because the dimension of each head is reduced to 64, the total computational complexity remains equal to O of n squared times d. The mathematical operations required equal running a single head attention layer with the full 512 dimensions. By restructuring the data pathways, multi-head attention decouples representational depth from computational cost, achieving a highly granular analysis for the exact same processing price. After processing, data exists as 8 separate output values, each with a dimension of 64. To move forward, the model must return this data to the base 512-dimensional state, so it can pass through the residual connections and enter subsequent layers. It achieves this through concatenation. The 8 64-dimensional vectors are chained end-to-end to reform a single 512-dimensional vector. But simple concatenation is just appending lists of numbers together.
To synthesize these isolated insights into useful data, the model executes one final linear projection. A parameter matrix multiplies the concatenated vector to produce a final, unified output value. This final projection acts as a blending mechanism. It gives the model a controlled way to weigh the importance of the syntactic features against the semantic features it just computed. The internal architecture of multi-head attention operates as a continuous cycle, splitting complex data into isolated metrics and intelligently recombining them into a single comprehensive token representation. Moving from theoretical architecture to empirical observation, we can look inside the network to see what these isolated subspaces actually learn in practice. By examining layer 5 of the encoder stack, we can trace how individual attention heads map connections between specific words in a sentence. One specific head has learned to perform anaphora resolution. It tracks pronouns to their distinct antecedent nouns, mapping a strong, singular connection from the word its directly back to law. This visualization shows an entirely different head in that exact same layer. Rather than tracking pronouns, it has learned to isolate long-distance verb dependencies. Notice how it connects the word making across several intermediate tokens to complete the structural phrase making more difficult. These distinct tracking tasks occur at the exact same time, without the weights of the pronoun map influencing the weights of the verb map. This visual evidence proves that the individual projection matrices successfully force the network to isolate and learn entirely distinct linguistic rules. To see why this matters, consider the counterfactual. Processing this same sentence through a single, massive attention head. The sharp, highly confident weights for the pronoun tracking and the distant verb dependency would be forced into a single softmax function. The mathematical consequence is forced averaging. The structural precision of the verb dependency and the semantic precision of the pronoun mapping would actively dilute each other into a flat, generic distribution. Projecting the data into lower dimensional subspaces physically prevents this dilution by giving each calculation its own isolated coordinate system. Because the dimension of each head is simply the total model dimension divided by the number of heads, this gain in representational capacity is achieved without adding temporal complexity to the training cycle. By structuring the attention mechanisms to run concurrently, the transformer reduces training time compared to older, sequential models. Multi-head attention solved complex sequence transduction not by adding raw computing power, but by providing mathematically isolated pathways that capture the multifaceted nature of human language.